I want to speak about my recent work with my collaborators, and this work is about a theorem. We tried to prove the following result. I will announce the result, and the most of the talk I will be talking about something else. But let me at least announce what would be a goal of what we thought would be a goal of our paper. We wanted to prove that if you have a scale invariant field theory, which I will abbreviate as SFT, scale invariant field theory, and scale invariance should be understood broadly. I will not actually define it technically, although potentially I could. It just means that you have an invariance under homogeneous rigid rescalings. It's less strong a constraint than a conformal symmetry, because conformal symmetry means that you can do Poincare moves, right? You can rotate, you can shift, and you can rescale. But besides that, in conformal group, you have special conformal transformations. Here, we don't have special conformal transformations, just the intuitive and descendant scale invariance. Scale invariance plus unitarity imply that the theory is secretly conformal. This is secretly an SFT. And the idea was to prove that in 4 dimensions. Apparently, methods and techniques change, and that will be probably the most important topic I will discuss here. This result is known in 2D. It was not known in any other dimensions, although people thought that it should be correct. Now we try to prove it in 4D. We don't know how to do it in 6D, which just means that the technique depends a lot on dimension. Now, I would like to say, well, even less success, I would say, even less success. Sorry, yeah. That's right. The technique will change a lot on dimension, but for all even dimensions, you might hope to have some similarity, and for all odd dimensions, you might hope to have some similarity. There is almost no technique which would work for both of them, except maybe for methods based on entanglement entropy. But I will not talk about that today because it definitely will run out of time if I do that. So what I wanted to say to begin with is that we thought that would be a theorem, but I really hesitate here, especially in this audience where people are very mathematically inclined, that this is a theorem. Because if it's a theorem, it means that if I have SFT and unitarity, and we have a proof, it means that if we have this and this implies this. But we don't have a proof because we have a counterexample. And as Vasily pointed out to me once, it's not that my proof is wrong. It's just that the initial assertion is wrong. So for mathematically inclined people, what I'm saying is an absurd. But because we're also physicists, I suggest we think about this as some sort of a Schrödinger cat. We have a proof, and we have a counterexample. If you want to squeeze me and get to the bottom of this, I will try to reformulate this result in the following way. This is not a proof in a conventional way. It's just that we reformulate this theorem in a slightly different way. We say that if you have SFT and unitarity, we can prove, let's say on a physical level of rigor, but still we can prove that some other property is satisfied. I will explicitly explain what this property is. And then it's very intuitive to think that if this property is satisfied, the theory is SFT. But so this property is to say that some S matrix, I will define it later, is trivial. This is some auxiliary S matrix. Don't think about what it is before I define it, because obviously in CFT there is no S matrix, so that's not the CFT. That's not an S matrix of this field theory. But this auxiliary property is satisfied, and this link we can prove. I would think. Now a jump from here to here is very intuitive. I don't know any mathematical way to prove it. It just I cannot think otherwise. But we have a counterexample which actually shows that there could be a situation when this is satisfied, this is not satisfied. So if you wish, you can think about our result in the following way. We reformulated this idea in a different language, and now one has to understand the connection between this and this. Okay? So that will be a fair account of things. So now I would like to explain, first of all, why this is a question worth thinking about. So maybe like 20 minutes I would like to speak about 2 dimensions. And even before I do that, so this is all moving, right? Even before I do that, the idea here, the more general idea here would be to study very general, very fundamental properties of quantum field theory. So these properties, let's speak about two dimensions, because two-dimensional case is something people in this audience know very, very well. In two dimensions, we have a homologic of C theorem, which says that if you have a RG flow which starts with some CFT and it goes into some other CFT, then you can, at this point in the UV fixed point, you can associate a number called central charge to this conformal field theory. That would be CUV. And here it will be C infrared. And we know that the flow between this point and this point is monotonic, such that CUV is larger than C infrared unless the RG flow is trivial, so there is no flow at all. So this is irreversibility of RG flow. This is a completely fundamental result. It doesn't require specification what kind of field theory we are talking about. As soon as you have some basic axioms satisfied, such as Lorentz invariance and so on, locality, then this result takes place, right? So we want to understand something similar. Well, not only people wanted to understand for a long time something similar for other dimensions, and in other dimensions there is a similar ideas or similar conjectures, some of them proven, and I will speak about that today. But I want to emphasize that this is like some very, very general properties. And the idea of thinking about this theorem, of this assertion that scale invariance implies conformal invariance, should be understood as a part of this general picture. Because we want to understand what is the possible quantum. If I have Lorentz invariant quantum field theory, how complicated could it be? What are the properties? So if I have this picture and I have this theorem taking place, and in two dimensions this theorem takes place as well, it's called sometimes it's called П.Л.Чебышева theorem. Which says that SFT basically implies CFT. Then it means that any field theory originates from some CFT, right? And it means that this flow cannot go forever unless I go, if I don't allow my couplings to become infinite, such that I go to some other map in the space of couplings, then this flow cannot go forever, because not in this way or in that way. I cannot have circles like that, and I cannot have a limit in cycles. And I have to stop somewhere, and whenever I stop, that would be a CFT. It cannot be, when you stop, that's by definition scale invariance, right? And it cannot be just scale invariance, have to be CFT. So in two dimensions, we understand that CFT is the most basic, most general building block, and theoretical, if you understand it very, very well, and as far as I understand, part of the goal of this conference is to understand two-dimensional CFTs very, very well, then at least conceptually you understand all two-dimensional field theories, because whenever you have a two-dimensional field theory, it's just a result of having a CFT and perturbing it by some relevant operators. Okay, so that's a general picture. So the conceptual goal behind all those questions is to understand this picture in higher dimensions, right? So maybe I should emphasize that. So the general question is to basic properties of QFTs in D larger than 2. Right, so this is one very basic idea. And another basic idea which is emerging along the way when you try to prove results like irreversibility of RG flow, or you will try to prove the result that SFT implies CFT, if you try to do it in dimensions larger than 2, another idea emerges. It's more technical, but maybe on this level it is technical, but maybe if you start digging in, it will be more conceptual. I couldn't uncover anything, although I tried. So I will present it in a technical way, but it seems to me that this is a fundamental question here. And the question is the following. We firmly believe, or at least I firmly believe, that Euclidean formulation of field theory is as good as Minkowski formulation, especially when you talk about mathematical properties, fundamental properties of quantum field theory. And in theoretical physics, especially not when we calculate scatterings of real particles at LHC, but when we do theoretical physics, we very often forget if we work in Euclidean space or Minkowski space, and there are numerous examples when we don't really account for that, because to go between the two, you usually say a proper analytic continuation will do the trick. But the idea here is that it might be that Euclidean formal language might not be equal to Minkowski language. Now, I will be more specific about this. Yes?
What do you mean? I mean, there's a theorem called
Yeah, I will mention that. Yeah, we will be very specific. I'll try to explain that there is an example. It's a very known example. It's from the paper by Dubovsky et al., I believe, with Nima Hamed and many other people. When you have a property of theory in the Minkowski space, and you can prove it in one line, and there is no known proof of the same property in the Euclidean space. So I'm running out of time as of this moment, but I hope I will mention that, right? And Osterwalder-Schroeder theorem doesn't help with that. Okay, so these are two conceptual questions which I would like to understand. I will not understand them today, but at least this is something I'm thinking about. So let me start with a two-dimensional case, because I need to remind you. So this was the most coherent part of my talk when I was presenting the questions. Now I will try to give you like a bunch of ideas or a bunch of examples we know about all this, but they're not very coherent, because it seems like we don't have an underlying picture or principle or method how to think about these questions, and we do things on a case-by-case basis. Sometimes we can prove something, sometimes we cannot, but it seems like we don't understand the general picture. Therefore, my talk will be a bunch of those small pieces. Each piece, I hope, will be coherent, but you might have an impression that the whole talk is not very coherent. This is just because I cannot present it, I don't understand it in a coherent way. So let me start with something we understand very, very well, a two-dimensional case. A two-dimensional case is very simple, and it's very special because it's very, very simple. So I will start with the proof of Zamolodchikov theorem. When I say Zamolodchikov theorem, I mean that CUV is larger than CI infrared. In mathematics, a proof, in this case, this is a proof. It's a mathematical proof, as you know very well. But I will not prove it the way how Zamolodchikov did it. I will do it in a slightly, much less powerful way, but in a way which will be more convenient for me later. Usually in mathematics, when the proof starts with a word, let's consider something, this is just a nice way to explain what is going on, but this is not an explanation of an idea. An idea has to be explained somehow else, right? There's quite often is an idea behind an explanation or a proof, but in mathematics, those ideas are either explained somewhere else or not explained at all. In this case, things are very simple, because I will start my proof with the words, let's consider a two-point function of stress energy tensors, and that's the whole idea. The whole idea in this case is just to consider this particular object. As soon as you consider it, within a couple of minutes, if you're knowledgeable enough, you understand that this object is very simple and you can derive a lot of things, right? So this simplicity fails you later, because when you go to 3 or 4 dimensions, you don't really know what to do. You can consider two-point function, and people did it, but it doesn't help. So unfortunately, very simple proof in 2 dimensions is not something which we are very happy about. So let's consider a two-point function of the stress energy tensors in a momentum space. And apparently, this whole thing is controlled by only one function if you require conservation. You require conservation of the stress energy tensor. Then there is only one scalar function which governs this guy. I will slightly change the conventional notations and introduce this function p squared. So p squared I will denote by s. Okay? So there's only one function, and that's the simplicity of the story. Here I also assume that the one-point function of t mu vanishes. I can always introduce the counter term such that the one-point function vanishes. Now in the C of t, f is proportional to the central charge multiplied by s. Okay? Just that simple. Okay? So now if I want to calculate delta C, which is CUV minus C infrared, I just say this is f prime at infinity minus f prime at 0. Okay, that I can always do. And let me also notice that I introduced f in such a way that f of s equal p squared is just the 2-point function of the traces. And throughout this talk, t without indices is just t mu mu.
Sorry, why 1-point function? Why 1-point function?
We can always, because of
For the trace.
1-point function. Because of the Lorentz invariance, we can always say that this is g mu multiplied by some constant, and then we can introduce the counter term, the cosmological constant. Yeah, you can always modify your theory by introducing the introducing the counter term, which is simply square root of g lambda minus lambda, and this lambda will cancel this lambda.
You work in flat space.
Yes, I work in flat space.
Huh?
I'm working at flat space. So sorry, this is two-dimensional flat space. Oh no, correlators are written in two-dimensional flat space.
And what is Sj in front of CT? What is S with index? Proportional to C times S.
S is this. Just by definition, S is p squared.
But the trace may have anomalous dimension, right?
No. If you
Trace?
yeah trace no stress energy tensor cannot have anomalous dimension.
You're talking about conformal field theory.
I'm talking about conformal field theory. What other field theory? In scale invariant field theory, also you cannot have anomalous dimension. Okay, so let's calculate this. Now, if I have this 2-point, yes?
Why is the correlation function of the trace is also there?
Excuse me?
If you can calculate the correlation function of trace t and trace t, we will obtain 0 again. But why? It's not conformal field theory.
You mean why this is 0? Huh?
Yes, for
It's not-
trace t.
It's not 0 yet. It's some non-trivial function f.
But if we take the trace of both stress and adjutant.
No, we will not get 0. This is in 2 dimensions, right? So if I take trace of this, I will have minus p squared, right?
Okay.
Wait a minute, but if you have trace, I don't understand. You're writing this for conformal field theory or for...
No, this is for general. This is for a general. This formula is true for general field theory.
I'm saying that for a general, you can manage to have 1-point function 0.
Yes, you can always modify your theory by adding the
The trace of Helmholtz momentum tensor may have anomalous dimension once again.
I don't even know what is the dimension for the general non-conformal, not scale invariant field theory.
Whatever, but so the trace has anomalous dimension.
I don't even know what dimension is. Before we talk about anomalous dimension, I don't even know what dimension is.
How do you kill it by contact?
Well, again, the 1-point function of t mu by Lorentz invariance is g mu multiplied by some constant lambda, right?
This constant is dimensional.
Yeah, it has some dimension, yes.
So what do you mean? What is dimension?
Dimension 2, I suppose. It's just a constant. It's just a dimensionful constant. It has dimension 2. Now, I can always introduce a counter term square root of g lambda, and I make, m, and I take lambda plus m equal to 0. That's it. Let me move on. This is really trivial.
I'm saying exactly that for t mu, for trace,
Yeah.
this is not true that lambda has dimension 2, yes?
I don't even know what you say when you say dimension. I'm saying something completely trivial. Take your theory defined by a partition function and add this term to a partition function. This is a counter term. You can always add it. Well, generating function. Partition function is a functional dependent on external metric, whatever. Add this guy and calculate t mu now with the new guy. You will have this formula, tune m plus lambda to be 0. I want to move on. This is really not a conceptually important point. Believe me, this trick accomplishes what we need. Okay, now we want to calculate delta c. And because f is a 2-point function, I can use a Cullen-Lemon representation, which is in this case the same as dispersion relation. I can simply write down that f as a function of s is an integral of ds prime, s minus s prime, imaginary part of s prime, right? Are you with me with this formula? This formula is kind of important. This is just a Cullen-Lemon representation or dispersion relation. There is nothing complicated. I just used the fact that f has certain analytic structure. Now, if I try to calculate f prime at infinity at f prime at 0, what I will have here is an integral over ds s squared imaginary part of f. F is a two-point function. F is a two-point function, so imaginary part of a two-point function has to be non-negative. And therefore, I have the following result. Difference between CUV and C infrared is an integral of non-negative quantity, so it's non-negative, it's positive. In this way, I prove the Zamolodchikov theorem. It was simple, and that was the point. Yes?
I don't understand the first formula.
This formula? So, do you believe me that I can take the one-point function to be 0?
Suppose I believe.
Sorry, I addressed this question to Nikita.
Suppose I believe that.
I lost my audience. Now I have to work one by one. And by the way, I will answer this question, but please let me move on. So how to derive this formula?
This
Yes.
formula is written for any theory on the RG flow.
This formula is written for any Lorentz invariant field theory such that d mu t mu nu equals 0. To write this formula, you do the following. You write most general tensor which corresponds to the symmetries. You use the special identity which is true only in two dimensions, which kills the other possible structure. In general dimension, you have an exchange by scalar particle and by spin 2 particle. So there are two structures. This is the exchange by scalar particle, which is the only surviving piece in two dimensions. And it's dictated simply by transversality.
I don't understand that if I work in CFT, then
yes.
the stress tensor, the trace has to vanish.
Exactly. So let's look and see how it works in the CFT, right? So that's a good question. In a CFT, I claim that f is just a polynomial, right? C is central charge multiplied by s, by p squared, right? What does it mean? It means that in a CFT, if I have two-point function of traces, this time I will write like this. P minus P, this is just C P squared. Yes. This is a contact term, right? This is a contact term. It's a polynomial without anything. So if I go to the coordinate space, I will have Tx, T0 is equal to delta function. So unless x is equal to 0 at the separate points, I have 0. And that's exactly the point that you can translate it in the following language. T acting on vacuum is 0. Okay? Oops. So which means that T as an operator is 0. And the contact term is that, yeah, well, that was the part of my story. Thanks for asking, because in this way I just explained this part of the story. Another important part of the story, which I also want to speak out, is the following. This is not a conventional representation of delta C in two dimensions. I'm sure you saw it in the coordinate space instead. So let me write it in the coordinate space. In the coordinate space, it works like this. You have delta C, and you can just do Fourier transform of this, and you will have d2x, x squared, t of x, t of 0. Okay, f is a two-point function here. So you can trust me that I did the transformation from coordinate space to momentum space correctly, but this is not the point. The point here, which I want to emphasize, is the following. In two dimensions, I can write in coordinate space or in momentum space. I have two languages, and both seem to be completely identical, just related to each other by a Fourier transform. The positivity of this integral is coming from the positivity of the imaginary part of this diagram, and this is in two dimensions exactly the same as the reflection positivity in coordinate space. And again, this is one integral done with the Cullen-Lemon representation. So the Osterwalder-Schroeder theorem for two-point function is trivial, because it just says that if you have imaginary part of f larger than 0, so I want to emphasize that, so I want to write this as the following formula. Imaginary part of f larger than 0 is exactly the same as to say that this state has positive norm, okay, with anything, right? So, well, maybe we should write something like nt has positive norm, and that's exactly the same. And this is called Cullen-Lemon, and this is called Osterwalder-Schroeder. This is the same as to say that you have reflection positivity. which is formulated in the following way: Tx, T0 larger than 0. So all languages agree, and you just need a Fourier transform to go from one to another. This is wonderful in 2 dimensions, but when I go in 4 dimensions, everything will fall apart. Okay. In 2 dimensions, you also have the C function, not a theorem, but C function. This is a much stronger statement, and I don't have any conceptual explanation why you have a C function, besides, again, those words that, well, everything is so simple, and you have only one variable, and you can integrate ordinary differential equation, because you have only one variable. But I'm not sure if these words explain anything. So this is just a gift that we have this function. I will not talk about it too much. Let me spend, you see, I'm trying to accelerate because this was supposed to be just an introduction. But there is one important thing. I proved the Zamolodchikov C theorem. That was easy. Let me also prove that in 2 dimensions, scale invariance implies conformal invariance. OK? Maybe I will make a small break. So far, everything was simple, I hope, right? Well, maybe you forgot how to go between those 2 things, but let me assure you that this is truly just a Fourier transform. This is not complicated. So let me try to explain how we can prove that scale invariance implies conformal invariance in 2 dimensions. Again, it will be too simple to learn something meaningful. Okay, so the proof will be in 1 line. Again, I go to this formula and I say, what is f? F has dimension 2. So in a scale invariant theory, so I have S of t. In a scale invariant theory, f is a function of s, could be either alpha s or alpha s log s divided by mu, just by dimension. Okay? Well, ask me why I cannot have log squared. Well, the logic here is very simple. The question is that scale invariant? Oh, first of all, this is obviously scale invariant, right? Because it has canonical dimension 2. So this is OK. But this is too good, because this is, in fact, CFT. Nikita asked me this question, and I proved that this is CFT. Because if I have f is just a contact term, then I know that my t is 0. And t0 is a CFT. OK? So this is not only SFT. This is, in fact, CFT. Can I have something like this? Naively, this is not scale invariant. But let me try to convince you for a second that this is still OK. OK? Let's remember what f is. This is 2-point function. And if I try to see if this formula is truly mu squared dependent, I can try to differentiate this 2-point function with respect to log mu. And I will see that the derivative is just a contact term. I change the scale, and my correlator changes by the contact term. Contact term is not physical. Or at least you have to prove that this particular contact term is physical. So if I consider a correlator at 2 separate points, for example, if I consider d over d log mu, t at x, t at 0, that will be just 0. So naively, this is scale invariant. Okay? If you have log squared, that will not be the case anymore. That's why you cannot have log squared, for example. Log is the only function you can have. Okay? But this was not the full story, because somehow I started working with the traces, and indeed at the level of traces, this formula seems to be OK. But if you take the full formula and you plug this guy into the full formula, you will immediately notice that although this guy is OK, d over d log mu t01, t01 is non-zero at x and at 0. OK? So it's a 1-line proof to say that simply there is nothing you can write such that all observables, all correlator separate points would be scale invariant. End of story. It was too simple. Pelchinsky had to write the whole paper about this, not because of this, but because he had to prove that what you think intuitively as a scale invariance is mathematically what you would define as scale invariance. Because it might be that scale invariance could be realized in a more complicated way. For example, you have an operator which is an operator of scale invariance, but the way how it acts is a complicated way. For example, it's non-diagonal, and you have log mu's coming. It's more, I don't want to spend time on this, so it's more like a logarithmic CFT, right? If those words tell something, that's good. If they don't, just maybe it's good to read П.Л.Чебышев's paper, make your own opinion what is written there. Okay, so that's all I wanted to say about two-dimensional case. It's good time to ask questions, because now I will try to build on this, and I will try to learn. I will try to use those lessons which I learned in 2 dimensions. And one point is that in 2 dimensions, unfortunately, everything is so simple that we don't even know what to bring in higher dimensions. And as we go in higher dimensions, we will see that many things fall apart. For example, Euclidean language and Minkowski language is not the same. I forgot to say, coordinate language, this is less conceptual, but coordinate language doesn't seem to be the same, as powerful as momentum language. And so on, so on. Okay, so any questions? No questions, good.
Why?
Why? Why what?
Why coordinate language is equal to momentum?
Okay, we will see.
We will see, all right.
We will see. Oh, one more thing about 2 dimensions. Let me nail it with. Let me nail this proof with yet another language, which in 2 dimensions seems to be completely, well, it's not absurd, but completely unnecessary. There is yet another way how you can achieve all these results, and it's mathematically equivalent, but it seems like you're introducing too many things which you don't need. But we will need those things later on. Okay, so once again, in 2 dimensions, what I could do, I know the answer, right? From many, many different ways, I know the answer. Delta C is equal to the following integral in the momentum, in the coordinate space. Okay? Now, I want to derive it in a slightly strange way in 2 dimensions. I want to say, let's consider the partition function as a function of external metric, right? And we know how metric couples to stress energy tensor. By definition, when you change metric slightly, that's exactly the change. You change the theory, but the stress energy tensor. Okay. So if you're only interested in traces, and here you have only traces, what you can do, you can say, let's consider W as a function of tau, where we define tau in the following way. We just say that G mu is a flat metric multiplied by a while factor. Okay? And now we'll try to calculate this quantity for a flow which goes between 2 CFTs. Apparently, this is not so complicated as it sounds in the most general case. But to explain that this is not a complicated task, not to calculate it, but to calculate important pieces which we will need, is apparently much easier than you might thought. I don't want to do it in a mathematical level of rigor. I will try to do it step by step such that you understand from where I got this answer, and we will postpone until my talk all the questions related to that. Let's assume that instead of having this picture, I have a picture when I have CFT going into mass gap. And let's assume that this CFT is a very special CFT without an anomaly. Okay, if I have CFT without an anomaly, this very special non-anomalous CFT, it means by definition that delta omega, that omega at G mu multiplied by 2 sigma is the same as omega at G mu. This is the conformal, this is the definition of a conformal, one of the definitions of the conformal field theory, right?
So it means phi equals 0.
Excuse me?
So you mean the center?
Yes. It's not physical, just mathematical trick, right? It's just a mathematical definition of what CFT is. But this symmetry, that would be a mathematical definition of what conformal symmetry is. This symmetry is anomalous, so you have an anomalous term, but I don't want to introduce it at this point. I will introduce it at the next stage. Now, if I have this zero anomaly CFT, which flows into mass gap, it means that this W, because it's a mass gap, this W has to be a local functional of G mu. Just a local functional, that's all I'm saying. So I will write the most general local functional, which would be r plus alpha r squared plus r cubed plus dr, whatever. Doesn't matter. What is important here is that this is a total derivative, and this starts with 2 derivatives and higher. No, sorry, this starts with 4 derivatives and higher. So,
There is also cosmological constant term.
huh?
There's also, since you have a mass gap, you also have cosmological constant.
Yes, but it has no derivatives whatsoever, and the constant and the cosmological term we can again remove, and we have to remove it by adding the contract term. By adding the contract term. Yes, this is the game we have to play. We have to add by hands the contract term, but this contract term is not dynamical because it's just a function of external G minus. Now, if we remember that that was a real CFT which has an anomaly, that means, one second, that I will have to write the Polakov's action. R manifest R. Yes? Yeah? Okay. So this is, in fact, the true answer, and here it would be C. This is, in fact, the true answer in a general flow like this. It's just that because I flow from one CFT to another CFT, here I have to write delta C. To understand why it will be delta C in the simplest way, just think about a CFT here, which is a direct sum of 2 CFTs. And one, it goes to the mass gap, and another stays unchanged.
So I don't understand. So W is the effective action in the external gravitational field?
Yes.
For some quantum field theory?
Yes, yes.
Why are you saying that this is for the RG flow?
Well, it's for this.
For any theory on your line, you have some W, or it's
No, well, it's actually for the whole. I have to integrate over all the. Yes, I have integrated over all dynamical fields. So it's for the whole flow. It's for the whole. Yes, it's for the whole flow. In your language. Okay, now what is important about this action is that this is the only term which has 2 derivatives. This term has 2 derivatives, but it's a full derivative, so it doesn't contribute. This term has 4 derivatives. Everything else will have 3 and more, and perhaps just 4 and more, because 3 derivatives is very difficult to write in a Lorentz invariant way. So if I rewrite it in terms of tau, I will have the following. Delta C d tau squared plus O of d fourth. Okay? This is enough, and if you remember now that delta omega, variational derivative of delta omega with respect to tau is t blah blah blah, then it's just enough, this formula is just enough to derive this. You just take 2 derivatives, that's how you will have t and t. This Laplacian you have to cancel by x squared, it's a trivial step. Okay, so in 2 dimensions that was forced. We already had 2 separate languages, momentum space, coordinate space. I somehow introduced a 3rd language which doesn't add something. But apparently in 4 dimensions, this language is the correct one. So now I have only 25 minutes left. So my plan is the following. I will now go into 4 dimensions. And I will try to speak about 4 dimensions. 10 minutes I will speak about irreversibility of the RG flow. And 15 minutes I will try to talk about SFT and CFT. And I think I will not have time for anything else. All right? Any important questions I can take now. Otherwise, we will just go into 4 dimensions and discuss A theorem. So A theorem is obviously not my paper. As you know, it's a paper by Komargodski and Schwimmer. But I thought I should speak about this paper because of 2 reasons. Apparently, the relation between SFT and CFT is related to the A/C theorem, not only in 2 dimensions, but also in 4 dimensions. It just happened to be so. It's very strange because in 2 dimensions, there's no conceptual relation between the 2. It's just the technique used in both proofs is the same. And in 4 dimensions, there is also no conceptual relation between the 2, but the technique used to argue, to prove both is the same. So I do not know what is the conceptual relation between irreversibility of the RG flow and the relation between SFT and CFT. But apparently, the 2 always use the same technique. That's what I know for now. So I will have to remind you how A theorem works in 4 dimensions if I want to speak about scale invariance and conformal invariance. So first of all, how to formulate A theorem in 4 dimensions. It was done by Cardy, and he noticed the following. In a conformal field theory, you know that t is equal to, let's say in 4 dimensions, you know that t is equal to, there is an anomaly, it's called A anomaly, and that's an Euler density, and there is also C anomaly, and this Weil tensor, okay? And people somehow understood, well, actually Cardi,
Expectation value.
it's just an operator identity, and a curve space. Okay, let's go into expectation value. Cardi realized that this guy is the guy you want to discuss. So let's calculate the expectation value for a theory calculated on a sphere. Okay, in this case, it will be just proportional to A because sphere is conformally flat, so this guy vanishes. And now here is a heuristic argument why this quantity will be monotonically decreasing along the flow. If you take the sphere of radius r and you try to differentiate this quantity with respect to log r, what it means, it's a Weil transformation, homogeneous Weil transformation of the metric. If you change the metric because of this formula, that delta L in this case will be delta G mu T mu, what will happen is that you will introduce another, besides this guy, you will introduce another T mu in the pre-exponent. So this would be an integral over the whole sphere of a 2-point function. Okay, so this is quite easy to convince yourself that this is indeed true. This is a 2-point function. There is a reflection positivity. It's non-negative. This is a non-negative expression. I lost a minus sign somewhere here, so it's non-positive. So I have, right, and this is A prime, right? So I proved monotonicity of a function. This is fake because of the contact terms. Because I have to integrate over the whole space, including the point x equals 0, there are contact terms which don't let me to go through with this logic. And in fact, if you calculate this function on a sphere, it will not be homogeneous because of the divergences related to this quantity. But at least that was his heuristic understanding of things, and it turned out to be correct in the sense that AUV indeed happens to be larger than A infrared. But to prove it was a complicated task for many years, and people intuitively understood that in 2 dimensions you had to work. The idea was to consider 2-point function. Remember I said let's consider a 2-point function. In 4 dimensions you cannot consider a 2-point function. As you see, this guy is quadratic in R, in a curvature, a Riemann curvature. So 2-point function simply doesn't know about A. Only 3-point function and above know about A. So here you either have to consider 3-point function or 4 or whatever. But 3-point function doesn't have any positivity. There is no positivity you can associate to 3-point function, at least not that we know of. So okay, let's consider 4-point function. But here we immediately have a lot of complications. One of them, in 2 dimensions, we had only one function governing the whole correlator. Here we will have hundreds, literally hundreds. So it's not possible to distill. We probably will have just a few positivity constraints and hundreds of functions. So it's not easy to distill A and say that A changes monotonically. And second, it's not even clear how to do positivity constraint. Now we have a Euclidean language which is based on Osterwalder-Schroeder theorem, and that's what I promised to speak about, but I don't have time to speak about this. But this language would tell us the following thing. If we have a correlator of x naught x, y naught y, t minus x naught x, minus y naught y, this has to be positive, non-negative. Right? So this is the reflection positivity. But apparently, and this is equivalent to say that T acting on vacuum has to be a positive norm state. But if you think a second about this, especially this form, you will realize, or this form, you will realize that this correlator has to be the full correlator, including the disconnected parts. So if we speak about diagrams, this guy means that this plus this plus this plus this is larger than 0. In the kinematic limit you want, these guys will dominate and they don't know anything about A. Only this guy will know A, and you will not be able to distill it from the whole identity. So it sounds like a technical complication, but unless you know how to go through, that's all. There's nothing you can say. Now, people knew for, I don't know, 7 years, maybe even longer, I guess some people knew for many, many years, that Minkowski language could be much more powerful than the Euclidean language. For example, if you have a low energy theory, d phi squared plus epsilon divided by lambda to the fourth, d phi to the fourth, and this is an effective field theory, right? Then you can prove using Minkowski language that this epsilon, and epsilon is a very, very small constant, such that your energies, you're working with the energies much smaller than lambda. You can prove that epsilon has to be positive using Minkowski language, and this is done in one line. You just say, I consider a scattering of 2 phi's into 2 phi's. The scattering amplitude, which will be called f, which is a function of Mandelstam variable s. It's a forward scattering. I can write down, I can calculate it in perturbation theory. This is equal to epsilon s squared divided by lambda squared plus higher corrections in epsilon. Epsilon is a small quantity. Plus higher corrections in epsilon. This is the perturbation theory. At the same time, yeah, I already said all. So at the same time, you can write the dispersion relation. And from the dispersion relation, you will see immediately it has to be positive, right? So this is, well, sorry, I calculated this quantity. Okay, so it has to be positive. I took derivative, so I put some power of s. So in Minkowski space, you can do it in one line. In Euclidean space, it's simply not possible to do it. You can use Osterwalder-Schroeder theorem, but there is no known way, and I can attest to that. There is no way published in the literature to prove positivity of this guy in Euclidean space.
You're just using unitaries, right?
Yes. So that means that.
So unitaries translates to reflection positivity.
Yeah. So you see some contradiction in this logic. So one possible resolution of this formal contradiction is either that the reflection positivity in Euclidean space is not everything what unitarity guarantees. Or another resolution, which I believe is correct, is that low energy questions are not translated into low energy questions in Euclidean space. In Euclidean space, if you use reflection positivity, you should be able to prove everything, but you might need to go into higher energies. Which means that in practical sense, if you want to stay within low energy field theory, then reflection positivity is indeed not everything.
It's just that when you talk about low energy theory, this is something which is formulated more naturally in Euclidean space.
You would think so. You would think so. But apparently,
in Minkowski space, it's I would say it's rather hard to understand.
That just makes this puzzle more interesting, I would say, right? But I think I presented a puzzle very, very clearly, and I can attest there is no resolution in the literature. Let's discuss after. But I'm making this as a statement because I did some research both on literature on the subject, and I know that there is no resolution.
When you compute the scattering amplitude, one loop, four loop, or
this one is just tree level. This one is tree level because if you have loop contributions, they will be suppressed by epsilon.
Just use the vertex from the Lagrangian.
Yes. The diagram is not this diagram. The diagram is this diagram. Okay. So sorry, I have only 15 minutes. I will not take questions from this moment on because I want to. I will take questions in the end. Okay. So the idea of Komargodski and Schwimmer was the following. They said there are hundreds of functions here, and apparently reflection positivity, the usual way of presenting unitarity, doesn't help, but this way is more powerful. So let's combine those ideas, and that's what they did. They said, similarly to this logic, they said, let's consider in 4 dimensions a functional which is just the partition function calculated on a conformally flat metric. Okay? You can use a logic which is very, very similar to this logic. And instead of having this action, you will have the following action. You will have delta A d tau to the fourth minus d tau squared d2 tau plus some coefficient d squared tau minus d tau squared plus terms which are six derivative, which have at least 6 derivative. So this is the effective action they found. Then they realized that if you say that you want to scatter tau particles at low energies, if it's at low energies, you can forget about this guy. If those particles are massless, and they're massless in the particular way, you just say that d2 tau is equal to d tau squared, which means that from tau, you have to introduce another particle, phi, and that would be 1 minus tau. And you just say that phi is the free field. And you write everything in terms of phi. So you scatter 4 phi particles. Okay, they call phi the dilaton. So if you scatter 2 dilatons into 2 dilatons, this term, which is not universal, will not contribute. This term will effectively contribute as the d phi to the 4th. And they immediately reduce their proof to this statement. Okay? So that was the method of Komargodski and Schwimmer, their observation. They said, let's calculate the effective action. Let's scatter 2 dilatons into 2 dilatons. And let's say dilatons are massless. So let's promote them to be a dynamical field. Then you immediately understand that low energy scattering of dilatons is governed by the anomalous term. And the anomalous term has to be positive just because you can write dispersion relation like Dubovsky and et al. Did. Okay, so this is their proof. Now, this is the foundation. I have 10 minutes from now. And I'll try to squeeze the proof of SFT implies CFT in this 10 minutes. Because it's actually not a complicated proof. We didn't do, in our paper, we didn't do anything technically complicated. And all what we did was basically to consider the right object. It's just that before us, most people were thinking along the lines of two-dimensional case. And let me remind you how that works in two-dimensional case. In two-dimensional case, you knew that the right thing to consider would be the two-point function. And you knew that the way to show conformality would be to show that this is 0. And that's what people desperately were trying to do. But this is not working in 4 dimensions or any other dimensions besides 2. Because even in the conformal field theory, you can have T equal a box of L, which simply means that T mu nu, it's an improvement term. D mu T nu minus D squared G mu nu. You can just shift your T mu nu into this guy. The theory still stays conformal. In 2 dimensions, you cannot play this game because L would have dimension 0, and this 0 guy is not physical. There could be, we could discuss if it's physical or not, but it's in a simplest way, it's not physical because it would initiate logarithmic divergences. So, but in higher dimensions, these L's are present. For example, in 4 dimensions, you can say, and then if free massless or massive scalar, you can just say L is phi squared, right? So because conformal field theory doesn't necessarily mean T is equal to 0, to try to prove that this is 0, to prove this is CFT is an overkill. You will never be able to do that. That's one thought. And second thought, let's forget about two-point function. It's apparently not working in higher dimensions. So our proof in 4 dimensions was based on the following idea. Instead of considering two-point function, let's consider another object. To prove a theorem, we consider 2 into 2 scattering. Let's try 3 into 3 scattering. That's a groundbreaking idea. Let's start with n inter n scattering. So, okay. Let's try to do that. Let's consider n inter n scattering. Well, let's actually start with 2 into 2, right? So we have 2 into 2 scattering, 2 phi inter 2 phi. And we know that delta phi prime was equal to ds over s squared imaginary part of phi. And this is positive. So that was the A theorem, right? This is delta A. Maybe like this. Maybe like this. I don't remember. At this point, I won't be able to restore that because it will take time. So that was the A theorem in a non-trivial RG flow from CFT to CFT. We say what happens if you have SFT instead. And if you have SFT, then by dimensional analysis, F would scale like S squared, right? which means that the full f would be alpha s squared log s. If there was no log, again, that would be a conformal field theory. But if there is a log, it means that this integral would diverge. I don't have time to discuss why I have SFTs and CFTs and CFTs and why I hide SFT here. You can modify this picture just to say that I have SFT, and all I require from this SFT is that it has relevant operator, and I can go into mass gap or CFT to ensure infrared regularity. That's all I need. It's a technical question. Unfortunately, I don't have time to discuss it. But if I can assure infrared regularity, then I will say, well, this integral diverges. At the same time, this is a physical quantity which I can define in the infrared. And therefore, there is a contradiction. So for 2 into 2 scattering, I have to say that in the SFT, imaginary part of 2 into 2 has to be 0. That was first noticed by Luty, Polchinski, and Rotazzi. But because they were discussing this quantity, they could only squeeze that SFT implies CFT in the perturbative vicinity of another CFT. I don't want to explain how they did it, but basically they were discussing this quantity, and that's where they stopped. They could not prove it in a general case. We decided to go in a general case and consider 3 into 3 scattering. Unfortunately, 3 into 3 scattering more complicated because you do have optic theorem, but you can hardly write something like that. You can hardly write a dispersion relation, because a dispersion relation, a diagram of this sort, would have a genuine diagram of this sort with a cut in the middle, plus it would have a diagram of this sort. Right? And then the imaginary part can come from here. And it's very difficult to control this imaginary part, so it's very difficult to write anything like this. But now, and I'm still within time, I will use a very simple mathematical tool. I will do things by induction. Right? I already know that 2-point function is such that imaginary part is 0. I think it was simple enough such that you could appreciate it. We can do it by induction. 2-point function imaginary part is 0. Which means that this diagram doesn't really contribute. That's the only diagram which contributes. So I can write a dispersion relation of this sort, and it will look exactly like this. It will be exactly the same delta A, because this effective action, it's absolutely non-perturbative in tau. It's perturbative in derivatives, but it's non-perturbative in tau. So I can write what the left-hand side of the dispersion relation will be. So delta A will be equal to ds over s cubed, imaginary part of 3 into 3. But again, if it has a log, that would be divergent. But in the infrared, I believe this is regular. That's my assumption. So I cannot prove anything for the rigid SFT, which doesn't admit any relevant perturbation. That's the limitation of this argument. But if I can deform my SFT, then I have to conclude that the imaginary part of 3 into 3 is 0. And then by induction, I prove that n into n is 0. And then it simply means that if I have a scattering of many of those dilatons into many of those dilatons, forward scattering is always 0, which means by optic theorem that scattering of many phi's into anything is trivial. So where is my original formulation? Okay, going back to the original formulation, I proved within time that SFT plus unitarity implies that scattering of auxiliary phi particles is trivial. So the S matrix for phi particles, not for the original particles within the CFT, but for phi particles is trivial. Okay, so now, can I prove that this means that the theory is CFT or not? Now, this is a little bit tricky, and I know a counterexample for that, but it's very intuitive and logical to think that in most cases, triviality of this S matrix implies that this is a CFT. What is this scattering amplitude? Scattering amplitude of many phi's means that I calculate this diagram. And remember, phi couples to traces of stress energy tensor. And it means that, for example, with forward scattering, I will calculate a correlator of this sort. So if, for example, I assume that T is a Laplacian of something, and I plug it here, and I remember that I take scattering on shell, then this is obviously 0. So if it's a CFT, fine, that's good. At least it works well. By the way, I need to assume that the theory is infrared regular, otherwise it will not be true. It could be singularities here. But it would be, so kind of I proved that this is OK. But now I need to argue that this is OK as well. This is more difficult because I don't have any formal way to do it. And we couldn't find any formal way in the literature. There was a lot of work done on analytic S matrix in 60s, apparently. Maybe we don't know something. Or maybe this question wasn't discussed. But let's assume that the following intuitive statement is correct. If you have a particle which is scattered trivially, and we know that scattering doesn't depend on change of variables, it's very intuitive and logical to assume that there is a change of variables such that this particle will be just described by a free field. Okay? So if we assume that, then I will be able to prove that this is correct. So what I have the original particle phi. I have a kinetic term. I have phi coupling to tau. And I have something else. OK, I know I'm running out of time. So now, if this is nabla L, box L, that means that there is another variable phi, which is var phi plus L, such that this whole thing can be rewritten as d phi squared minus dl squared. And in this case, this phi particle will be just a free particle which completely decouples. You can convince yourself that this is the only situation that this phi particle can be redefined such that it completely decouples. But I do not know the formal proof that if the scattering, the S matrix is trivial, then indeed there should be a change of variables. In fact, those people who work with S matrix, they specifically wanted to diverge from the language of path integral or local fields and everything. So I'm not sure that there is a theorem in the literature which would connect properties of S matrix and the possibility to redefine your microscopic fields. So this is, I would say, an intuitive statement. But if you believe that this statement is correct, then I just say that T has to be a box of something. If it's a box of something, then there is an improvement term which makes my theory CFT. I don't have time, but now I need to tell you the counterexample, right? Because apparently...
Let's do the question.
Oh, OK, sorry. OK.
Questions? What's the counterexample?
And the counterexample. That was there's no counter. It's a rigorous proof. OK, so the counterexample is very simple. Let's consider the free massless scalar. And we do have the improvement term and everything. But let's now just say that you modify the theory in the following trivial way. You say that phi is identical to phi plus constant, which simply means that you don't allow any operator without the derivative, which means that this improvement term is off limits. And that's all. You have a consistent field theory. The scattering matrix will be trivial, but there will be no improvement term which will make your theory a CFT. Now, naively, you would say that the resolution of this puzzle is also trivial. You have a subsector of the bigger theory, which is a CFT. So I removed the sector, and I basically violated the CFT structure. But apparently, this theory, the scalar with this identification, is dual, meaning it's equal to the theory of the free two-form. And if you speak about free two-form, then that's all. You cannot write phi squared. There's really no local operator phi squared you can write. And this is a contradiction. So you get as far as here, but going here is not possible, because in a theory of free two-form, there is literally no traceless stress energy tensor. So the theory doesn't have primaries, as you know. The theory is not conformal. So, but it's a very special contradiction, very special example, and I think it might be possible to say that it's possible to prove this step under certain broad conditions, which would nicely exclude this free two-form. But I do not know the words.
Well, I would say that during in the scalar language, your modification actually introduced the scale into the problem, because this constant which you put here has dimension of mass.
Well, I mean, okay, so there are two separate examples. There is an example when you have a discrete symmetry, so you have L, right, or you have M, right? If you have NM and N is integer, which means that this is a theory in a circle, yes, then this is not a problem because you let this theory flow in the infrared, and in the infrared, this property is forgotten, and you have the usual scalar with the shift symmetry, and the infrared theory is conformal.
No, but in order for it to be conformal, you have to generate the R phi square couple, because the free scalar is not conformal invariant. It's a conformally coupled scalar, which is conformally invariant.
Well, I mean, if you have a field theory, then it's in a flat space and conformally invariant.
You will not see that, but if you work on the sphere, for example, you will see.
No. We're not going in a curved space. In this case, it's just I understand what you're saying, but my definition of conformal field theory is slightly different, technically different. I'm just saying that you can add the improvement term.
It's the same thing. I mean,
yeah.
R phi squared is the same.
Yeah, that I understand. No, that I understand. But you want to couple your theory to metric in a particular way. I never bother how I couple my theory to metric.
It's from that, it's just obvious that if you introduce periodicity of phi,
yeah,
you forbid R phi squared term.
But if you, that's true. But if you, but if you flow to the infrared, the resulting field theory in the flat space will be the field theory with the shift symmetry as an infrared theory, and it will be conformal.
With the shift, no, I don't understand. The shift by what amount?
By any amount, because in the infrared field theory, all possible shifts by definition much smaller than m. So you don't see the scale. You need to take the infrared limit, right? You need to consider low energy. You have a non-trivial flow in this.
Have a gauge invariance in the infrared?
Well, I mean,
global symmetry or it's global symmetry?
It's a global symmetry. It's a global symmetry.
So
you have a vacuum which breaks your symmetry to begin with, right? You have to choose what your phi to begin with, and in this local minimum, around this local minimum, you can expand, and the expansion will be a free scalar, the usual scalar. So this counterexample with the circle, we believe it's not a counterexample. The only genuine counterexample is when you have any constant to begin with. So these are two distinct cases.
The constant.
Well, we can.
The constant has a dimension.
If it's any constant, then it has a dimension. Well, then you cover all possible scales, and it's indeed a counterexample. If you have a particular constant, you have m and 2m and so on, then you have certain scale. And if you consider your theory at a scale much smaller than that scale, conformality restores. Okay? So that's what we were trying to say. But yeah. I confuse you enough, I guess.
I think I'm confused because what stops me if I don't pay attention to global things, then what stops me to dualize to two forms in that case?
It will be, yeah, there will be a difference in a two-form language. There will be a difference with the gauge symmetry of the two-form, the quantization of flux of the two-form.
You said you work on a flat space. You don't see any quantization.
So you will have yes. No. You will have to worry about those things if you want to dualize. I suggest yes.